Well, we've been talking about Lewis structures, right? Drawing different Lewis structures, talking about the steps you need to follow so that you can draw a correct structure. And then we talked about some exceptions that help us figure out how to do structures that may not follow the regular rules. Couple of related topics to talking about Lewis structures is talking about the energy in those bonds. Okay? Obviously, when a bond forms, there's a certain amount of energy that would be required to break that bond. Right? I mean, if you've got two atoms that are sharing their electrons and that are really close together and have a reason to be close together because they're sharing those electrons that makes them very stable, they don't want to be pulled apart. And so to break that bond, to pull those atoms apart from each other, would take a certain amount of energy. We call that a bond dissociation energy. Now, if you look at some information about different bonds, so here's an example of some different bonds, and it gives their bond dissociation energy. And then it also gives the bond length, right? How far apart do the atoms get when they bond with each other? And we can actually tell a few things. We can gather some trends from this data, right? So let's take a look at what we have here. So let's start by looking at the example bonds that they gave us, right? They gave us an H single bond H and a C single bond H and a C single bond O. And then they give us a C double bond O and a C triple bond O. Right, so we can see the difference between those. And the same thing with a C single bond C and a C double bond C, C triple bond C. There's a CN, a ClCl, an N, OH, and OO. Now, they also give us then the energy we require to break that bond. So for instance, if you wanted to break the bond between two hydrogens, the single bond between two hydrogens, it would take 435 kilojoules, that's what the KJ stands for, kilojoules of energy per mole. I know we haven't really talked about moles and things yet, and we'll get there. It's just an amount. The key is we're doing a comparison, though, of all of these. So what I want you to do is I want you to start to look for trends. All right, so I have an H single bond H, takes 435 kilojoules per mole. A C single bond H is only 393 kilojoules per mole. Now, let's look at these three. C single bond O, 356. C double bond O, 736. C triple bond O, 1074. Do you notice a trend there? So, single bond only took 356, a double bond took 736, a triple bond took over 1,000. So, it takes more energy to break more bonds. Now, you probably would have thought that originally, right? But it's confirmed by this information, by this data here. We have evidence that that's true. So the more bonds there are, the more energy that it takes to break the bonds. All right, so that makes sense. Now let's look at bond lengths. Right, so these are all being measured in picometers. If you remember your metric system, pico was way small. Right, we're talking about trillionths of a meter. And of course, since we're talking about atoms, we knew they were going to be really small amounts of space. So bond length, remember, that is the distance from the center of one atom to the center of the other atom. The distance between them is the bond length. So H single bond H is 74 picometers. C single bond H is 109. CO is 143. C double O, 121. C triple O is 113. So here's another one where we can do a little comparison. If you look at a single bond and a double bond and a triple bond of the same atoms, what happens to the length? So the length gets shorter the more bonds there are, right? Triple bond is a shorter length than a single bond. So now we've learned something else, right? The more bonds there are, the shorter the bond length. Right? And that really goes back to the idea of what are they doing when they're bonding? They're sharing electrons. If you have a triple bond, how many electrons are being shared? That's 3 pairs of electrons. They really have to get very close together to share that many electrons. So even though these little pictures here are all drawn and they look like they're the same length lines, in reality, right, they represent smaller and smaller lengths as the more and more bonds you get. All right, so we've done 2. Let's look at one more. Let's look at the relationship between bond energy and bond length. Right. So again, let's take the single bond, the double bond, the triple bond one. So the single bond one was 356 kilojoules per mole, and it was 143 picometers in bond length. And then the double bond was 736 and 121. And then the triple bond was the over 1,000 kilojoules, but the length was only 113. So what's the last thing that we can say? What's the relationship between bond length and bond energy? So as the bond length gets shorter and shorter, what happens to the energy? More and more. So the shorter the bond, the greater amount of energy required to break it. I always think of this, I want you to think back to the days when you could actually hold other people's hands and hug them. Okay? Think back to those days, all the good old days when we could do that, right? So if you were to just simply hold somebody else's hand, right, and somebody wanted to come by and separate you from the other person, all they had to do is get your 2 hands apart from each other and they could separate you. That wouldn't be too hard to do. But now I want you to imagine that you're fully hugging somebody else and they wanted to separate the both of you. It would be much harder. It would take a lot more energy for that person to separate both of you while you were hugging because you're that much closer to him. And the same thing happens here. That triple bond is a short bond. Therefore, it takes a lot more energy to dissociate, to break it. So the bond dissociation energy is the energy required to break the bond. Right? And we learned that the larger the energy, the stronger the bond is. And in fact, we really learned a couple of other things, and you should write those down. I don't have them here, but you should write them down, right? So the greater number of bonds is the greater amount of energy to break it. We also said the greater number of bonds is a shorter bond. And then we said the shorter the bond, the greater amount of energy to break it. Right? So those are the 3 things that I really want you to get out of looking at this. All right, one last thing where as we talk about just straight good old Lewis structures. And that is this idea of resonance. So it turns out that in some cases, when you're drawing a Lewis structure for a covalent compound, that there might be 2 or 3 or even 4 different correct Lewis structures, right? Possible ways you could draw the Lewis structure that follows all of the rules, but is not exactly the same as the other one. Let me give you an example of this, okay? By the way, we call these resonance structures. So here's what I want you to do. I want you to draw the Lewis structure for ozone. Now, just a little reminder, right? For a Lewis structure, you got to follow the steps. First, figure out how many valence electrons total do you have in that formula. Then, figure out who goes in the middle. This one should be pretty easy to figure out who goes in the middle, right? You got 3 O's. Which one goes in the middle? Then you have to fill in with just single bonds to begin with. Then you give everybody lone pairs to make them happy. And then you do your questions at the end. Is everybody happy, right? And did you use the same number of electrons that you started with? And if you did not, you then have to go back and you have to start putting in double bonds or maybe even triple bonds. All right, so I want you to try to do that. So again, pause on your paper. I want you to go through and draw the Lewis structure for O3, for ozone, and see what you come up with. All right, so you've done that. You've got your ozone figured out. All right, here we go. Here's what this is going to look like. First of all, O is in group 16 in the periodic table. So it has 6 valence electrons, but there's 3 of them. So 6 times 3 is 18. So I have 18 valence electrons to work with. Now, what goes in the middle? We decided that was pretty easy. There's an O, and then there's an O. Which one goes in the middle? The O, right? So if O is in the middle and I have 3 of them, means the other 2 have to be on the outside of that. All right, okay, so now I got to fill in single bonds, right? So single bond here, and then I put lone pairs everywhere. Remember, just you put lone pairs everywhere you can unless it's hydrogens. Hydrogens don't need lone pairs. So I'm going to put lone pairs around this oxygen, around this one, and then around this one. Once I do that, I ask myself the 2 questions. First of all, did everybody get the 8 that they wanted? Does this oxygen have 8? Yeah, it's got 2, 4, 6, and then the bond counts as another 2, so that's 8. Does the one in the middle have 8? Yep, 2, 4, and then the 2 bonds, another 4, that's 8. And then this one has 8 also. So everybody's happy, that's good. Did we use 18 electrons total? Well, I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Not quite. I'm a little bit over what I should be. Now, oxygens can form double bonds. It's not like those fluorines we were talking about the other day that can't form a double bond. Oxygens can form double bonds. So we can solve this problem by adding a double bond in. Where do you put it? Do you put it between the O and the O, or do you put it between the O and the O? Now, you're probably saying to yourself, well, does it matter? I would say to you, no, it doesn't matter. You pick either one. It doesn't really matter at all. So if I pick this one here and I make that a double bond, remember, every time we add a bond in, we have to go back and erase a lone pair from both sides of that bond. So one from this oxygen, one from this oxygen. Got to go away. Now, re-ask yourself the questions. Is this oxygen happy still? Does he have 8? 2, 4, 6, 8. Yeah. Is the oxygen in the middle still happy? 2, 4, 6, 8. Yeah. This oxygen, of course, hasn't changed. That's 8 still. Are we to 18? 2, 4, 6, 8, 10, 12, 14, 16, 18. Yep. That must be the correct structure. But wait a minute. We could have put that double bond on the other side. You might not think that that's a big deal, but that is a different structure. If I told you that you have to draw this and the double bond goes on the left side, and then I told you to draw this and put the double bond on the right side, you do have to draw something different to make that happen, right? That is a different structure. So I would have to redraw this. Oh, there we go. How does that happen? I don't have any clue why that happens. Let's try that one more again. So I would have to put my single bond here, my double bond on the right side, and then fill in these lone pairs. I got that. And this one would only have those 2 lone pairs like this one did, right? It's sort of like almost like a mirror image. And in fact, resonance is kind of like a word that means like echo. So you get a very similar structure, but there's something just a little different about it. And it turns out that in real life, ozone goes back and forth between both of these. Right? And so what we have to do is we have to draw all the possible versions that could occur out there. If there's more than one place that you could put a double bond, then you must draw all of the possible versions, all of the resonance structures. Ozone has 2 resonance structures because there's 2 different places that that double bond could have gone. Right? That's what we mean by drawing resonance structures. Now again, does this happen very often? No. It's very few times where you find yourself having a choice as to where your double bond could have gone. Most of the time it doesn't happen that way. Okay? And there's the nice neat versions. Here's another example of that. Right? CO3 with a -2 charge. It's called carbonate. Of course, you knew that because you've already had your ions memorized for about a month now. So CO3 with a -2 charge, carbonate. When you draw the Lewis structure for it, it turns out that it needs 1 double bond. Do you put it between the CO, or do you between the CO, or between the CO? And you'd say, well, I could have put it any of those 3 places. Well, then you have to draw it 3 times. So this does come up occasionally when you're drawing Lewis structures. If you find yourself having a choice as to where to put certain bonds, then you must show all of the possible places it could have gone. Okay? So you'll see that on the homework, right? There'll be some of those places where you're going to have to do multiple resonance structures. All right? And so our next step after this, we're going to get into talking about the shapes of the molecules. And we'll talk about how to do that.